go. We are live. Okay, so let's see. Getting back to our elementary statistical inference, but prior to that, let's talk about this homework. So problem number 1 was quite easy. Just draw a table, and in that table, put the values. It is a lot easier to handle like that for me. So when you put them in a table, you add them, you have the marginal probabilities for x1, and you add the columns, and you have the marginal distribution for x2. Now you can see what's the probability that x1 plus x2 equal 1. You just look at that table where the sum is 1. You add the things that you find. That's here and there. So 3 halves plus 2 halves plus 2 12ths, please. That is 5 12ths. So then we had in this problem, we would answer the same way. So anytime actually you have 2 random variables that are discrete, it's easier to just draw that table and then read your answers from the table. So here it says probability is x1 plus x2 over 2, but it's discrete with 2 values. So I draw my table. 1 2 1 2. I put in the numbers that I get. 2 12, 3 12, 3 12, and 4 12. Then I add them to get the marginal of x2, and I add them to get the marginal of x1. And I can see that x1 and x2 have the same marginal distribution. So the distribution of x1 is equal to the distribution of x2, and therefore the expected value of x1 is the expected value of x2. The variance of x1 is the variance of x2 because it's the same distribution. Therefore, I don't need to do that computation twice. Expected value of x1 equal expected value of x2. And how do I compute this using my table? I don't need to do the double summations because I have the marginal distribution of x1. So that is 5 12ths times 1 plus 7 12ths times 2. Let's try my answer. It's way easier when you do that than to try to do the double summation. It takes less time. Then you go expected value of the square, go the same way. Square, 1 square 1, 5 12ths, plus 2 square 4, 4 times 7 12. Get your answer. And then you got expected value of x1, x2. This is the only way you can go there and just multiply 1 times 1 times 12, 1 times 2 times 3, 12, 2 times 2 times 4 12ths, and you add them. You get what you get. Once you're done doing that, they're asking you to say whether expected value of x1, x2 is equal to the product. That it's obvious 5 half is not 19 12 times 19 12. Now the last part, you didn't need to go compute it because this is made of things that you know expected value of x1. You know expected value of x2 squared. You know expected value of x1, x2. So you don't need to go again into the table to compute this. You just use the formula and then you plug in the answers that you got above. Any questions on these? Now the next one is how to find the moment generating function. And here, if you mistakenly don't choose properly the boundary, you'll end up with a contradiction in your work. You want to integrate, you draw that region, make sure you see the region of interest. Here, the problem says 0 is less than x1, less than x2, less than infinity. So it's that region. It's in that region that the random variable has a non-zero distribution. So I want to integrate dx2 dx1, the density times e to the t1 x1 plus t2 x2, because that is the definition of the moment generating function. How do I do that? Now I choose to integrate with respect to x2 first, and then with respect to x1. How do I integrate with respect to x2 first? I fix x1 and I draw a line through that region. That's how I explained to you. Draw the line through that region. It starts at x1, so you will integrate from x1 to infinity because it ends at infinity up there. And for every x1 that you fix, you can actually fix x1 from 0 to infinity because that's the range of x1 inside here. So it's integral from 0 to infinity, integral from x1 to infinity, and everything else is inside there. The rest from here is your calculus skills, how you integrate that. With respect to x2, this all is a constant. So you just integrate e to the t1 and t2 x2 minus x2. So when you do that, this is what you get. Then you integrate this thing with respect to x1, and you get that 1 over 1 minus t2 times t1 plus t2 minus 1 squared. Then all you had to do after that was to plug in 0 for t1 to find the moment generating function of x2, then plug in 0 for t2 to find the moment generating function of x1. And if at this point you want to plug in a number and you find a contradiction, that means your answer is wrong. Because you know that when you plug in the 0 for t1, you get the moment generating function of x2. And when you plug in 0 for t2, you get the moment generating function of x1. And in this problem, they exist. So you can't say you can't plug in 0, because if you cannot, then your answer is probably wrong. Does that make sense? All right, and then after doing that, you can see that the two things, when you multiply, are not equal. It's not equal to the m of t1, t2, and you should have awaited that because given the density that you have, the two random variables are not independent. Why are they not independent? Haven't we said in this class that two random variables are independent if their joint distribution is the product of the distributions? Huh? Why here are they not independent? And this is x1 times e to negative x2. It's a product of a function of x1 and a function of x2. Why are they not independent? And I claim they are not independent because this product is not equal to that. We had a theorem like that. If they're independent, the moment generating function is the product of the moment generating function. But here, it's not. But initially, the joint probability distribution function is the product of a function of x1 and a function of x2. Why are the random variables not independent? Was the theory wrong? I claim it is still true. The theory is true. There was nothing wrong with the lecture. What's the problem in this exercise?
These functions are not distributions. X1.
You still need to prove that.
Is less than x2.
It is related to that. You need to find a way to say that better. Because actually the theorem that was given to you in class can be modified in such a way that if the joint distribution can be written as the product of a function of x and a function of y, then they are independent. It doesn't matter whether they are distributions or not. But the problem is somewhere else. And she just pointed to something that in this problem is related to that. The issue that commonly is forgotten in that theorem is that the support of the two random variables are also distant. They don't depend on each other. And in this problem, the support of x1 and x2 is linked by the inequality x1 less than x2. So you can't actually split this here. What's that again? This here is not a product of a function of x1 and a function of x2 because the range of the first function is linked to the range of the second. Because technically here you would need to put I x1 less than x2, and I x1 less than x2 is not a product of a function of x1 and a function of x2. It's a function of x1 and x2 at the same time. You can't split them. Does that make sense? And because of that, these two random variables are not independent. That's an important moment. You make sure that when you're saying these random variables are independent because of this, you make sure you check the support. The joint support needs to also be the product of the support.
So we could tell without doing any calculations that it couldn't be.
Yeah.
independent.
Yep. Without doing any of this, I could tell you that this is the answer. Just by looking at that. Because otherwise, this wouldn't be true. If this function is equal to that one, then the two random variables are independent. It's a theorem. And based on the fact that looking at this, I already see that it's not going to be independent. So that quality cannot happen. All right. Any other questions on this? Let's move forward. So the next question was about two random variables that are continuous with a joint distribution f, and I'm happy that you guys decided to go and read the transformation, but it is not what was intended in this exercise, because the topic on transformations, I cannot cover it in this class as of now, because it requires something that I will need to go teach you before I come and do it. It's not a prerequisite for this class, so I didn't expect you to go and try to figure out those Jacobians and all those things. They're not necessary. So just using the things that we are used to in this class, we answer the question. So the joint distribution of x1 and x2 is this. y1 is x1 plus x2. y2 is x2. Let us use the joint distribution of y1 and y2 is nothing but the conditional distribution given that y2 is little y2 times fy2. That's the definition, right? This is the definition that was given for conditional probabilities and conditional distribution. So I just multiply by this to get that. Now, if this is true, y2 is equal to x2. So this is the distribution of x2. So this is fx2 of y2, correct? Random variables that are equal have the same distribution. So this equality holds because the distribution of x2 is the distribution of y2. They have the same distribution. It's the same variable. Now, here, y2 equal y2 is still standing. I didn't change anything there. The only thing that changed was replace this guy by fx2. Now you go to the next step. You look at that conditioning. What did I tell you we do when we condition on something? We assume that that thing is all we know, right? And when we do the study based on that thing that we know. So if it is given that x2 is little y2, that's all I know about x2. So I can replace that x2 by y2 because that's what x2 is. So I replace that and I still keep my conditioning because replacing doesn't do anything on that condition. That conditioning is still there. So this line is correct using the fact that x2 is little y2.
Send us this later.
Huh?
Can you send us the solutions later?
They are always posted on Blackboard. Now next, what do we do? This is a constant. Shifting a distribution by constant, does it change anything? No, it doesn't change anything. You just shift the value by that constant. So y1 fx1 plus little y2, because this is the difference is that this is no more a variable. This is a constant y2, a number. So if I want to find the distribution of x plus a, the probability that x plus a is less than x plus a, what is that?
Same thing on both sides.
It is same as probability that x is less than a, right? Sorry, less than x. So that's what I'm doing here by subtracting the y2 here, because that a is what the y2 is. So here, having plus y2 here is same as not having it, but having minus y2 inside, because it's a constant. I can shift the constant. And now when I pull that constant inside, the distribution becomes that of x1 given x2 equals y2. And so when you look at this now, conditional distribution of x1 given y2 given x2 times fx2, what is it? It's the joint distribution. By definition, joint distribution x1, x2, x1, x2 at the points that are given, y1 minus y2 and y2. That's it. So this is where you started, this is where you ended. So that distribution is equal to this. Any questions? All right, if there is no question, then look at the next guy. We still have a joint distribution. 21x1 squared, x2 cubed. Again, here you see that same condition, x1 less than x2. Otherwise, they would be independent. Because of this, they are not. And so the question is to find the conditional mean and variance of x1 given x2 equal little x2. How do we do that? We find the distribution, we find the marginal distribution of x2, and then we divide the joint distribution by the marginal distribution, and then we use it to find the conditional mean and conditional variance. That's why we're finding this. You get that? And then we get the conditional by dividing. So we get this with the condition, this with the condition that 0 less than x1 less than x2. You forget about this, the rest of your work is going to be wrong because you will not know where to integrate. You cannot integrate past x2 because x1 has to be less than x2. And so expected value of x1 given x2 is therefore integral from 0 to what? X2, not 1. Because you can't integrate past x2. x1 has to be less than x2. And that's why you get this. Expected value of the square, same way, you get that. And the variance is the expected value of square minus the square of the expected value. So you get 3/80 times x2 squared. And then the second part of the problem was asking to find the expected value of y and the variance of y, and then do a comparison. I see many people had some issues here. The question is not asking you to use a theorem. It's actually to verify the theorem at this point. So you need to get that distribution of y, use that definition of the distribution to find the expected value of y and find the variance of y. And then compare what you get to the expected value of x that you can compute and the variance of x that you can compute. It's not about a theorem. All right, next problem. I've seen that many people did a lot of work here with all those sums again. And then I will repeat the same advice. Whenever you have these three distributions with numbers, draw the table. Put the numbers in there. Put them 0, 1, 2, 0, 1. Put the probabilities inside. Find the margins on the corners. And then you start your work. What did the problem ask? Find the conditional means and variance. The conditional mean of x1 and the conditional mean of x2, right? So what do? I'm the kind of person that doesn't like to go around with too many fractions that I want to simplify or do anything with. I put the things down. Each of them gets simplified, and then I start working. So I take this. From this table, if I want the conditional mean given x1, I turn this table into the table of conditional distribution of x2 given x1. How do I do that? Take each of the probabilities divided by the probability of x1 of the given, in this case, given column. So this is the joint probability. I divide by the probability of x1 that is here, what is here. When I do this, I get the conditional probability. So I take 1/18 divided by 418. That's 1/4. 418 divided by 718. That's 47. 618 divided by 718. That's 67. This is the conditional distribution of x2 given x1 equal 0. And I go to the next line, I do the same thing. I divide 318 by 418, I get 3/4. 318 by 718, I get 3/7. 118 by 718, I get 1/7. And this is the conditional distribution of x2 given x1 equal 1. So when you do that, now you want to compute the expected value of x2 given x1. You can just continue in that table, draw one more line. Expected value of x2 given x1. And to each of the columns of x1, 0 times 1/4 plus 1 times 3/4. 0 times 1 of 47 plus 1 times 37. And 0 times 67 plus 1 times 17. I don't need to see how you're doing those. That's not really what we're teaching, right? So I don't need to see the details. If I'm seeing the table with the correct numbers, I know you're doing it, right? Huh? 6/18 divided by 7/18. 118 divided by 7/18. You're dividing everything by what is below.
But now what is below 7/18?
What does this have to do with the distribution of x1? That's the marginal distribution of x2. This row has nothing to do with the work that is happening here. It has to do with what is happening here. Now you have to find the distribution of x1 given x2 here to find the expected value of x1 given x2. And you do the same work that we just did here. Now dividing by this column. When you divide everything by this column, you get this. And then you compute the expected value the same way we just did here, and you get the two values. Again, that is based on the fact that the conditional distribution is the joint distribution P x1, x2 over E of x2. This is the distribution of x1 given x2. So you take the probabilities which are inside, you divide by the corresponding probability of x2, you have the conditional distribution. So you do the same thing for x1, you have the conditional distribution. And that is 1, 2, 3, 4 tables. It's a lot less than doing computations on 2 pages, right? Any other questions on this? But I'm not saying that if you take your 2 pages and do the work, you don't have the result. I give you the points, but you spend more time. That's the thing. Okay, now the next one. In the next one, it has to find mu1, mu2, sigma square 1, sigma square 2, rho, then answer some questions. So, and then this table was given. And again, I see it's discrete distribution. The first thing that comes to my mind, hey man, just draw your table. I change that table to the one that I'm used to. I draw my table, I put those probability in, add them, get the marginal of x1, add them, get the marginal of x2. Now I get the expected value. 3/5 times 1 plus 2/5 times 2. That's it. Then you get to the next one. You want to find this expected value. Okay. 1 times 315 plus 2 times 515 plus 3 times 715. That's it. So I have the mean of x1, mean of x2. For the square, all I need to do is square the headings. So 1 square, 1. 1 times 3/5. 2 square, 4. 4 times 2/5. That's 8/5. Add them, you get your answer. Do the same thing for x2. Square the headings, multiply by probability in add. 1 square, 1 times 315. 2 square, 4 times 515, 2015. 3 square, 9 times 715, 6315. Then you get the answer. Now you can do the expected value of x1, x2. Multiply the headings, multiply by the probability, and add. You get that? Then you find sigma square 1 by the formula, sigma square 2 by the formula, and rho as the covariance divided by sigma 1, sigma 2. So you get that. Now, the next question asks you to find the conditional mean of x2 given x1 or x given y, depending on the names that you gave to the variables. It doesn't change anything in the answer. So whenever they say conditional like this and it is discrete, I go right away there. Draw the table and I find the conditional probabilities. That's a table of conditional probabilities that I get. How? It's given x1, right? So I go to this table, given x1, so I'm going to divide each of the numbers in here by the corresponding entry of x1, not x2. So the corresponding entry of x1, which here In this case, it's 3/5. So you divide that by this by that, this by that, this by that, this by that, this by that. And you have the conditional distribution of x2 given x1, which is what we have in the table. Then you do the probability, the expected value. How do you do the expected value of x2 given x1? When you have the table, you just go to take the value of x2, take the corresponding value of x2 multiply by the probability, take the value, multiply probability, and add. Same thing for the second. Take the value, probability, value, probability, value, probability, and add. So you get that. Then the next part was write the equation of the line of the expected values was y equal. Now the mu plus this is rho sigma 1 over sigma 2 over sigma 1 times x minus mu 1. When I do this and I don't use a calculator, things simplify down to this. And when I plug in the numbers, k expected value of x2 given x1 equal k, they satisfy the equation. Any questions on this one? Are we clear on how I obtain the conditional probabilities to quickly answer the question? Okay, so the next problem, this is the problem where I guess many people had issues because forget to draw the graph. And I always tell you, when you don't draw the graph, you are 80% chance of getting the things wrong. The problem says the density is 1 under condition that y is between negative x, and x is between 0 and 1. Draw that space. Negative x less than y less than x. You got to draw y equals negative x, y equal x, x from 0 to 1. That's it. So this is the region of interest. Get that in front of you before you start answering the questions. Now the problem says, get the expected value of y given x. To get this, you need to have the density of x. Marginal density of x, that's why we compute this. X is, y is between negative x and x. So if I integrate with respect to y, it will be integral from negative x to x. So I get 2x under the condition that x is between 0 and 1. 0 otherwise. This is the part where the problem is saying on a set of non-zero measure, because it's not everywhere. It's not for all values of x that this answer is correct. It's for x between 0 and 1, and the measure of this set is not 0. Okay. If I fix x equal, if I say expected value of y given x equals 3, that expected value is 0. If I say expected value of x given y equals 2, that expected value as well is 0. It's no way equal to what is written here. So you need to always make sure that you remember what's the range that you're working with the problem. Now, if I want to find the distribution of y, and this was the most difficult, you want to integrate with respect to all values of x, all possible values of x. Get to that graph. How did I tell you you find the distribution? You draw a line. You fix y, and you draw a line that goes across the region. And when you look at this thing, you can see that if you draw a line here, you meet this. If you draw down here, you meet a different line. So you can't force the two things to be in one if you don't think carefully. But when I look here, If I fix it here, what I'm getting here is negative y, which is the absolute value of y here, because y is negative. If I fix it here, I start at y, which is the absolute value of y. So I'm always going to be integrating from absolute value of y to 1, from absolute value of y to 1. That's why it's integral from absolute value of y to 1 of dx, and it gives you this. Under the condition that absolute value of y is less than 1, because x is less than 1, therefore the range of y, that's it right there, 1 and -1. The range of y is -1 to 1, not 0 to 1. So after computing that, now you have the distribution of y, you have the distribution of x. If I want the expected value of y given x, I will integrate from -x to x, not -1 to 1. Because y is always between -x and x. I will integrate from -x to x, y times the joint distribution divided by the marginal distribution, which is 1/2x dy. This integral, when you integrate, that's y squared. It's going to be 0, and I just, in general, I wrote here as integral of an odd function over a symmetric region. There's such a theorem in calculus, 2 ideas. When you integrate an odd function over a symmetric region, you get 0, no matter what the function is. No matter what the boundary here is. If it's symmetric, you get 0. But in this case, you can just integrate and plug in x and then plug in some, but sometimes you cannot even integrate, but you know it's 0. That's the thing. So that's the reason why I wrote this, because sometimes I might give you a density that you cannot integrate, but knowing that, you can still say that the integral is 0. Then for the second part, expected value of x given y will now be equal to integral when you have x, when you have y, sorry, and you want to integrate, you want to integrate with respect to x, knowing that y is fixed. Check this. If y is fixed and up here, x goes from y to 1, right? If y is fixed and down here, x goes from -y to 1. So again, that is from absolute value of y to 1. That's why here it's integral from absolute value of y to 1 of x, which is the variable you're integrating. And now the joint density divided by the marginal of the thing you're conditioning on. That's 1/1 minus the absolute value of 1. Now, when you integrate this, that's x squared from 1 to absolute, from absolute value of y to 1. This is what you get. So this is 1 minus y squared over 1 minus absolute value of y, which is either 1 minus y when y is negative or 1 plus y when y is positive, between 0 and 1. Now, the conclusion where you had some confusion is that this function is not a linear function. Right? Go 1 minus y or 1 plus y, so it's like a triangle. It goes like this. And this one expected value of y given x is a linear function, because the function 0 is linear. What does it mean, linear? Ax plus b. So conditional distribution of y given x is 0. It is linear for any x between 0 and 1, which is a set of non-zero probability. This one is not linear for y between -1 and 1, which is a set of non-zero probability. So that's explaining the part of the question that was talking about set of non-zero probability. Any question on that? There was a lot of trouble on this question. Any questions? Do you have any question on that? Does it make sense? All right. The next question was about independence. So here, simple. We know that two random variables are independent if the joint distribution can be written as product of distribution for all values of x and y in the range. So the range is from 1 to 4 for x1, 1 to 4 for x2, so there is no problem. The range of x doesn't depend on y, and the range of y doesn't depend on x. And now all you need to do is form the table of probability. And it's always best to, again, draw the table. We said everything is 116, so I fill the table with 116 everywhere. And then I add everything to find the marginals. And once I'm done, I can see clearly that everywhere it's 1/4, 1/4, 1/4, 1/4, 1/4 times 1/4 is 116. And for any number, for any cell that you will take here, the probability, the joint probability is equal to the product of the marginals. Therefore, the random variables are independent. Now, the last two were the easiest one on the sums of random variables. Just find the expected value, and then knowing that when you have IID, the expected value of the sum is the sum of the expected value. So you get this, the variance of the sum is the sum of the variances. So you get 4 times the variance of 1. And here it was just linear. So sigma square is A squared, sigma square 1 plus B squared, sigma square 1, and B was 1, A was 3. So you get that, and you solve, you get K equals 7. I guess that was the easiest problem of the homework. All right. Any questions in general on this thing? We are done with the homework, and we are moving away from this topic actually. Is there any question on anything that we have done till now?
That matrix stuff on the test.
Huh?
The matrices.
What do you mean?
Like, by the time you drawing matrices, is that stuff going to be on the test?
I wrote the description of the test that clearly says that it is covered by the test.
I have a question.
Yes.
I do really understand. One of them was why that you did that in the range. I don't understand how you get why. What's up with why?
Where?
Yeah. Yes. The F of y. It does why there's that one.
Yes.
Yes.
And that's the graph.
It's starting at those diagonal lines.
X is from 0 to 1.
I know.
Okay, and if X is from 0 to 1 and Y stops here, what's the value of Y? And up there. That's why Y is between -1 and 1, which is absolute value of Y less than 1. Absolute value of Y less than 1 is same as -1 less than Y less than 1. Or is it not the question that you were asking?
between the 0 and 1.
If it's not the question you're asking,
That's
could you
the question,
specify
just
for me
to
to
get-
understand?
So, try to get it.
This line is y equals x. So when I'm here, x is 1, y is 1. This is y equal negative x. So if I'm here, x is 1, y is negative 1. And that is the range of y that is related to this set here. Anything else? So if I ask any question on this assignment now, everybody will be able to give me 100 because there's no question. All right, let's move on. Under the assumption that everybody now knows what this is about. And we will be talking about this now. Some elementary statistical inference, that is chapter 4. And again, for the question that Annette was asking earlier, the matrix thing that we are talking about is the multivariate normal distribution. And I can say again, that's part of your test too. Make sure you know how to do that. There's no way you're coming out of a statistics course and you don't know how to handle the multivariate normal distribution. That would be a big issue. Though I didn't put many of them on your homework assignment. Read the ones that are done in the lecture. If you want to learn more, you can do the problems that are in the book. I can only assign as many problems as I think it's possible to do in 1.5 weeks. If I add the problems with the normal, people will complain. All right, so let's say we are talking about a typical problem. So we are finally entering statistics. What is the typical statistical problem? You have a population. Which we denote X. X has, let's say, PDF or PMF. X has a distribution that is not null. And we need to figure out how to use it to make decisions. It's strange, right? So you have a population, has a distribution. You have no idea what that distribution is, and you want to use that distribution that you have no idea about to make some decisions that will apply in some people's lives. And your question is, how can you do that with the most, how can you do that in the most accurate fashion, the most accurate way, such that when people actually get out there and do what you're telling them to do, it works for them, though you don't know this distribution here. For example, people are going for the elections, you have 16 candidates. In my country, sometimes it's up to 25. And you want to have the odds or the chance that one specific candidate wins. Right? The population of interest is everybody that is concerned by that election, every person that is eligible to vote. And the distribution is the probability that every specific person that goes there is going to vote for the person that you're talking about. And you want to get his chance of being elected. And you go out there and you ask a single question to everybody, making sure that nobody's answer is influenced by somebody else. You sample maybe 100, 200,000, depending on how rich you are, because sampling will also involve money. And then you get the answer from them, you collect those answers, and you use those answers to figure out what will be the percentage of each of the candidates. That's all. That's one model that goes into this. And in general, that's what we do in statistics actually. So you take the problem, you find a parameter that is in there that you want to estimate and you want to use it to decide. After your study, you would say candidate one might win with 70%. And my error that I'm making on this estimation I'm giving you is 1%, for example. So 1% of the time I might be wrong, but it can 99% of the time, if I run this election under the conditions that are given here, this guy is going to win with this probability. Okay. So now we have two common cases. First one is there is absolutely no information about distribution. In this case, what you will be doing, we call that a non-parametric statistics. So you have no parameter in that distribution, you just want to work with it without assuming anything. And in the second case, the distribution is known up to a parameter. Meaning that the distribution that you have there depends on a parameter that you don't know, and your job will consist of estimating that parameter. Once you have an estimate for that parameter, you have an estimate for the distribution, and you can use it to do whatever you want to do with it. To conduct work here.
You're below the screen.
Thank you. So without any work here, you need to sample some, usually what the word for this is observations. From the population. Usually that's what you will see as X1, X2, Xn. You say you sample some observations from the population. Why? because you cannot use the entire population is too large. So you need to get some observations. What people like the most is when your observations are independent and identically distributed, and we call that a random sample. So when you read the problem and you see a random sample was selected, from now on you need to know that means that the observations are independent and identically distributed. They are independent and they have the same distribution. That's what you call the random sample. It's when you have x1, xn, I, d, which means independent for the first I and identically for the second I, and distributed for the d. So we say you have a random sample if you have observations that are independent and identically distributed. Notice that I'm not more saying random variables, right? I'm saying observations. Though they are random variables, it's things that I go out here and measure. And the second thing that you might need is a statistic. It's a function of the data that does not depend on any, very important, parameter. That's a new word I just succeeded in putting in here, is that one. Data. What do you call data in statistics? It's the set of observations that you're working with. So when you're reading a paper, you might find people not talking about observation, they're talking about the data. It's the same thing. Right? Here, for example, T of x1, xn, which is x1 plus x2 over 2. This is a statistic. So any function of the data that does not involve any parameters is a statistic. T2, x1, x2, and this is usually a very big deal for some people, not understanding the difference between what is a statistic and what is not. If I say mx1 is x2 over 2, this is not a statistic, because I have no idea what m is. Does that make sense? So that's a parameter in here. That disqualifies this function from being a statistic. Because if I want to work out, I might want to know what that m is. So a statistic doesn't have a parameter, only the data points, the the random sample that is used in it. Any question on this? All right, we are about to get serious. Now, another definition, new word, an estimator. First time we are putting that word down. An estimator of theta, which is called the parameter, is a statistic that is used to, new word, but friend, estimate, right, based on the data. What is this guy? An estimate. Usually we are confused between these two, between the estimator and the estimate. An estimate of theta is the value of the estimator for a given sample. So what they call an estimate is when you actually got out there, you already have your sample and you plug it into that estimator. That's what you call the estimate. So you're not going to write x1 plus x2 and you're going to tell me this is an estimate. That's an estimator. The estimate is the numbers that you got out there to collect. When you put them into the estimator, that's what gives you an estimate. So T equals H of x1, xn is an estimator. If this is an estimator of theta, then little t equals h of little x1, xn is an estimate. We say that an estimator T of the parameter theta is unbiased. If the expected value of T is equal to theta. Example, let's say x1, xn is the random sample from Bernoulli with parameter p. T1 equals x1 plus xn over 2 is an unbiased estimator of P.
So if you go out there and you select n observations from the independently from the Bernoulli distribution, I take the first and the last, I add them and divide by 2, I get an estimator of P that is unbiased.
Why? Expected value of T1 equals 1/2 expected value of x1 plus expected value of xn. What's the expected value of x1?
What?
I can't do it. There's no thing that is P. What's the expected value of x1? It's written x1 up to xn is a random sample from Bernoulli P.
P. And this is the part where I tell you, my friends, you need to know what is in the notes. You need to know the expected value and variances of each of the distributions that has been given in this class. Otherwise,
You'll just be dreaming from now on.
because it's going to be used, it's not going to be computed. It says Bernoulli, you know the mean is P.
So I say, what's the expected value of x1? x1 is from Bernoulli, so the expected value is P. xn is from Bernoulli, the expected value is P. So that's 1/2 of P plus P, that's P. The expected value of T1 is equal to P, and that's why T1 is an unbiased estimator.
And there are many estimators of P. It's not only one.
That's why we say it's an.
And billions of them. I can define anything that will have expected value equal to P. That'll still be an unbiased estimator of P.
Notice here I took the first and the last, I add them. If I add all of them and divide by n, x1 plus x2 is also an unbiased estimator. You prove it the same way. Each of them has expected value P. You add them, divide by n, you get P. Example 2. If I take x1 out to xn, the random sample from, say, Poisson distribution with parameter lambda.
Can you give me an unbiased estimator of lambda here?
Which means any function of x1, xn that has expected value equal to lambda.
That last part.
x1 up to xn is a random sample from the Poisson distribution with parameter lambda. Anyone give me an unbiased estimate of lambda in this case? And actually the question, what is lambda for the Poisson distribution? Huh? The mean, is it all? And the variance. It's the mean and it's the variance. So, and the good thing is the one that we're going to use is the fact that it's the mean. If it's the mean, then technically any of them is an unbiased estimator. Any average or weighted average is going to be an unbiased estimator. So in this case, if I define T3 equals A1 x1 plus A2 x2 plus AN xn such that A1 plus A2 plus AN is equal to 1. So these are numbers, okay? Not parameters to make this not be a statistic. It is a statistic because these are numbers. I'm saying take these numbers, any numbers such that the sum is equal to 1. Expected value of T3 is going to be equal to lambda. So T3 is an unbiased estimator. Of that. So on that being said, you can see that there are billions of unbiased estimators out there. And so if you want to conduct this study, are you just going to be guessing around, picking anything and working with? That doesn't make sense, right? Because it seems from one sample to another, from one estimator to another, things change. Your decisions will be changing. So what do? That's where in statistics, we start defining rules to choose an estimator based on some properties that we want. Find the best estimator under certain conditions. Let's say I want the variance, for example, of that estimator to be as small as possible. That's one way to think of it. Another way would be say, let's choose that estimator in such a way that my data that I obtain is obtained for the most likely value of that parameter. So if I have a sample that I already got, for what value of my parameter is my data the most likely? So that's one way of finding that. Say, okay, I'm finding the best possible data. But when you will be doing that, when you solve that question, what you will get will be a function of the data, which will be a statistic, which in most of the cases turns out to be also an unbiased estimator. In that case, you say, oh yeah, so I got an estimator that is not only unbiased, but is the best possible guess of theta for this data that I have based on the distribution. Does that make sense? That is what we call the maximum likelihood estimation, which we will be talking about next time. I'm just going to put the definition down today. Next time, we'll talk about that. So for the time that I have, I'm just going to be pointing some common mistakes that sometimes people have here. Maximum likelihood estimation isn't only done for IID data or random samples. No. All it says is you want to maximize the likelihood
given your data. And that likelihood doesn't have to be the product of distributions. It's the product of distributions only if you have a random sample. Is that clear? So let's say we have two observations, x1 and x2. That are linked by the joint distribution. That's one. Two. Two pi. Sigma 1, sigma 2, square root of 1 minus rho squared. Negative q over 2. This is q not 9. Where q is equal to 1 over 1 minus rho squared x minus mu1 over sigma 1 squared minus 2 rho x 1 minus mu1 x2 minus mu2 over sigma 2 plus x2 minus mu2 over sigma 2 squared. This is the bivariate normal distribution where when the correlation is not equal to 0. So the random variables are not independent. Let's say we have this, and x1 and x2 are linked by that. This is the joint distribution. And the question could be, find the MLE. This thing is called MLE, maximum likelihood. Find the MLE of U1, U2, rho. One MLE of U1, U2 under sigma squared
sigma 1 squared, sigma 2 squared, and then 1 and e of u1 on the fixed parameters of.
If you have to do that. So MLE doesn't always entail that you have a random sample and then you just multiply the distribution, then you answer the question. So if you're asked to answer these questions, what you need to do in the procedure is, in case 3, because it is 1, everything else is 0. Most of the time, instead of maximizing this formula, we minimize negative log likelihood. And the answer is the same. So define L of theta as the log likelihood of the likelihood function. In this case, this is the likelihood function. When you take log of that, what do you obtain? That's going to be negative log of sigma 1, negative log of sigma 2, negative 1/2 log of 1 minus rho squared, and then when you take log of this, you get minus q over 2, right? That's what you get. That's the log likelihood function. Then do the derivative of that function with respect to, and theta in this case, that's mu1, because I'm considering case 3, so that's mu1. So everything here is a constant with respect to mu1. So it has absolutely no effect on the work that you have to do. And all you need to do is to take the derivative where you have that mu1. And where you have that mu1 is right here. So that derivative is going to be 1 over 1 minus rho squared, and then you take the derivative, you get 2 over sigma 1 times x1 minus mu1 over sigma 1 sine. Then you take the derivative here. When you take the derivative here, what happens? This is a constant, and 1 here turns into negative 1. Minus and minus is a plus, so plus 2 rho over sigma 1 times 2 minus 2 sigma 2. And the derivative of that is 0. And you are going to set this equal to 0 and solve for mu1. And then you solve for mu1. So what you get out of here, solving for mu1, is what you call the maximum likelihood estimator of mu1. Given that everything else inside there is fixed. Yes, sir. What? Respect to mu1 and second. The derivative of this function with respect to mu1,
That's it written here. I don't understand the question. Mu1. The same mu1 that is here. It's L of mu1. That function. We are taking the derivative of this function. Thanks. So this is the function you're taking derivative of with respect to mu1. Okay, solving for mu1 here is easy, right? That goes away. 2 goes away. So you get mu1 equals x1 plus sigma 1 over sigma 2 x2 minus mu2. Right? And then when you solve this, you put a hat on it. Do you see that? Do you remember seeing this thing somewhere? Do you remember seeing this formula somewhere? And homework problem, right? That's where it comes from. Because when you fix mu2, that's how you would estimate the mean of the other variable if you have only one observation. Now, if you have many of them, imagine if you were to multiply several times, then you had a huge work to do. So that's what we'll talk about next time. Thank you for your time today.